Greetings and welcome to the complete lecture for Chapter 5 of Chemistry 221, which is entitled Advanced Theories of Bonding. In this section, we will look at the two main theories of bonding that are used by chemists a lot. One is called valence bond theory, and the other one, which is shown there on the picture on the right, is molecular orbital theory. And we'll look at both of these and see if we can figure out what's going on. Pretty exciting chapter. All of the theories we're going to look at in this section, though, basically want to answer the same thing, and that's how do you go from atomic orbitals into molecular orbitals, or the orbitals of molecules? And it's kind of a more interesting question than you might think. Like, why do the figure 8 p orbitals, which are shown in the upper left-hand corner there, or the spherical s orbitals, which is that big blue thing there, how do you turn at best 90-degree angles into the 109-degree angles that VSEPR geometry predicts so well? So the question really is, how do you go from these atomic orbitals to the orbitals that are in molecules? And both theories, both of the main theories we're going to talk about, attempt to answer this question in their own way. So the two main theories of bonding which are used in chemistry, the first one's called valence bond theory. Valence bond, or VB theory, was first proposed by Linus Pauling, who was actually one of the great Oregon chemists. Pauling went to Oregon State University before going on to get his PhD and lots of stuff. He's a fascinating person. But anyway, Linus Pauling in the valence bond theory basically proposed that the valence electrons, those outer electrons on atoms, are localized between atoms, or they can be lone pairs for that matter. And each bond that forms is basically one electron from each atom. Those electrons overlap, and they form then bonds that are stabilized by two nuclei. And valence bond is really great for normal kind of operations, which is cool. We'll talk about that. But the other theory, which is a newer theory, is called molecular orbital theory, or MO theory. And Mulliken there was the person that first kind of got this ball rolling. And basically, in molecular orbital theory, he also was talking about valence electrons, but the valence electrons are delocalized over the entire molecule into what he referred to as molecular orbitals. And we will draw in this section some of those molecular orbitals, which are seen right there. At first, it might look a little bit strange. I completely understand, but we're going to make sense of all of this. So hang tight while we talk about valence bond theory first, and then we'll talk about molecular orbital theory. Now, a sigma bond, or a single bond, is one of the bonds we talked about when we draw Lewis structures. And you can think about a sigma bond as basically having two atoms that overlap. And then they overlap in just the right amount, you actually make a pretty strong bond. So on the far right there are two atoms at quite a distance away, and there's no overlap, there's no interaction. And as the atoms get closer, i.e. as you go right to left, first you have a partial bond, like some overlap and some attraction, but then you get to some kind of ideal place where you have the maximum attraction. And that's what this part here shows on the picture. That shows the ideal spot where you have the maximum attraction. However, if you start getting too close to each other, then the protons start repelling the other protons, and the electrons can't help but start repelling the other electrons. So there will be places where it gets too close. So you want to have like the Goldilocks effect, all right? Not too close, but not too far, just some kind of ideal part. And when we'll talk about energy in a future chapter, the energy of the bond can be predicted, and so can the bond length, which is really cool. So this is the interaction between two 1s orbitals to make hydrogen, H2. And again, it forms this sigma bond. So sigma bond you can literally think about as the orbitals getting close enough to interact. There are other kinds of sigma bonds besides s orbitals coming together. So the top represents the two 1s orbitals of two hydrogen atoms to make the H2 sigma bond. And you can see they get close enough, they start to stick together, and that's what makes the bond. It's kind of like if you have a handshake, all right? You want to have an ideal length between the two people. You don't want to get too close into the personal space, but if you're too far away, the hands can't make contact. It's kind of a silly analogy, but it does work. But that example uses two 1s orbitals. And in chemistry, we've definitely seen where 2p or even 3p or higher orbitals can come together. So the second example there is where hydrogen's 1s orbital connects to a fluorine's 2p orbital. Now, one of the orbitals on fluorine has a single electron. If you remember from the electron configurations, fluorine is 1s2, 2s2, 2p5, and that 2p5, those 5 electrons are distributed over 3 orbitals. You can have 2 2 electrons per orbital. So what that means is one of the orbitals has only a single electron, and that is the orbital that's going to bond with the hydrogen. And like before, the orbitals have to get close enough so they bond to make the sigma bond, no problem. But you could also have, in the last example, two 2p orbitals, or two 3p, or 4p, etc., etc. And when they come together and get close enough, they start to interact. There becomes an ideal distance between them. So sigma bonds can form between any kind of atomic orbitals. Just depends what you happen to have in the molecule as of this time. So let's consider boron trifluoride, BF3. And in the last chapter, when we drew Lewis structures, we saw that boron is one of the atoms that can be under an octet. So it's happy with 3 sigma bonds to fluorine, no problem. Doesn't have an octet, but boron's okay with it, as well as aluminum, beryllium, etc., etc. Now, boron is 1s2, 2s2, 2p1. It has 5 total electrons. And if you think about this long enough, the 1s and 2s orbitals are like big spheres, like balls. All right, there's no angles at all. And the 2p orbitals are 90 degrees apart from each other. So you have like a 2px, 2py, 2pz, and they're all 90 degrees. So how in the world do you go from, at best, 90-degree orbitals into the trigonal planar 120-degree angles that we saw through VSEPR? And that's kind of the real question that drives both valence bond theory and molecular orbital theory. How do you go from one to the other? Because right now, it certainly doesn't look like you could have that possible. So Linus Pauling said that in order to make this work, you have to have what he called orbital hybridization. And you can think about hybridization as being like a mixing of orbitals. So if you look on the left-hand side, the above orbitals represent the atomic orbitals, the 2s2, 2p1. And in the bottom, what he tries to show then is that 3 of the 4 orbitals, and again, there's 1, 2, 3, 4 atomic orbitals, and 3 of them hybridize, or they mix together, and they become what he called sp2 orbitals. So instead of having a 2s and 2 2p orbitals, you end up with 3 sp2 orbitals. So you can see where maybe this came from. The sp2 means 1 part s and 2 parts p for sp2, and each of those has a single electron in it. Now, one of the p orbitals was not hybridized. It's unused, and we'll talk about why that's important. But anyway, in valence bond theory, hybridization means you're mixing atomic orbitals to make equivalent energy molecular orbitals, if you will. The hybrid orbitals are nothing more than things mixed together, all right? And when they mix together, they become all the same energy. And if they're the same energy, this will be important to us pretty soon. Like 2s was lower energy than 2p, but when you hybridize them, they all become the same energy. And if they're all the same energy, then they'll want to be as far apart from each other as they can. This is where the 120-degree part kind of pops in. So in this case, 1s and 2p atomic orbitals gives 3 sp2 orbitals. And that's again where this comes from. So sp2 means 1 part s and 2 parts p. And there's going to be 3 of these, as well as that unused p orbital that we'll talk about later. So this picture shows the results of kind of all the stuff that happens here. So in the first box there on the left-hand side, those things are the sp2 orbitals. And they look kind of like mushrooms to me. I don't know if that works for you, but that's kind of the best way to describe. This is all based on math and stuff, which we don't need to worry about. But those 3 sp2 orbitals, you can see they're all at 120-degree angles because they're all the same energy. They all want to be as far apart from each other, and that's what happens. So then if you keep going to the right, on the far right would be the boron trifluoride molecule. The fluoride 2p orbital, those atomic orbitals, come in contact with one of the 3 sp2 orbitals to make a sigma bond. So you can see here how the bond, those sigma bonds in BF3, the boron has an sp2 orbital that connects with a fluorine's 2p orbital. They make that kind of overlap to make the single bond, and it's pretty cool. orbital. So why hybrid section works is that it understands, it justifies, if you will, why the VSEPR model works. It takes the atomic orbitals and hybridizes them into these hybrid orbitals. And in this case, you end up with 3 hybrid orbitals. They're all the same energy. They want to be as far apart from each other as they can. That's where the trigonal planar part comes in. And then the single bonds that form, the sigma bonds, they come from an sp2 orbital and the fluorine's atomic orbital. So a couple of takeaways from this. If you ever are asked what the hybridization of the central atom in a molecule is, the trigonal planar geometry always means sp2 hybridized, all right? Trigonal planar only results as a result of sp2 hybridization, and that's really an important thing. We're going to see the electron pair geometry will allow us to assign these hybridization terms, just FYI. The second thing is that it's only the central atom which is hybridized. The outside atoms continue to use their atomic orbitals as before, so it's only the central atom where the quote-unquote magic happens, and magic, of course, being in this case hybridization to make these valence bond orbitals. This shows, again, a kind of a summary of all the things going on here. In the middle part, it shows, again, the 2s2, 2p1 atomic configuration being hybridized into 3 sp2 orbitals with that unused p orbital that we'll talk about later. So it's the boron which is hybridized. So that's why if it says, what is the hybridization of boron in BF3, or even sometimes this, what's the hybridization in BF3? If you see trigonal planar, that means sp2. Because sp2 means you have 3 of these hybridized orbitals. They're all going to be as far apart from each other. The outside atoms just use their atomic electron orbitals. So the outside atoms just use 1s2, 2s2, 2p6, that kind of stuff. Let's look at another example, this time from methane, which is CH4. And again, the same kind of question. How do you go from carbon with 1s2, 2s2, 2p2 atomic electrons, how do you go from there into 109-degree angles as predicted by VSEPR, i.e. the tetrahedral electron pair geometry? And like before, what Pauling said is that in valence bond theory, the central atom orbitals are hybridized, and at the same time then they end up being the same energy, so they all want to get as far apart from each other as they can. And if you have 4 electron clouds, they definitely want to be in tetrahedral arrangements.
The valence orbitals of carbon are the 2s orbital and the 3 2p orbitals. When these atoms form methane, their orbitals are thought to hybridize to form 4 equivalent orbitals. Because each hybrid orbital for the carbon atom is composed of 1 part s orbital and 3 parts p orbital, they are called sp3 orbitals. The energies of the hybrid orbitals are the average of the original atomic orbitals.
So I like this video a lot. It shows how you take the 2s orbital on carbon and the 3 2p orbitals on carbon, and you hybridize them. And again, hybridization just means you're mixing them. And I also like in this video how it showed how the 2s orbital went up in energy and the 3 2p orbitals came down in energy. And at the end, they were all the same energy level. All right. And this is important because in science, you're not supposed to create or destroy any energy. And you're just rearranging the energy to make them all the same value. And once they are all the same value, they want to be as far apart from each other as they can. That's where the tetrahedron arrangement comes from. So when you make a CH single bond, like in CH4, that single bond is a result of an sp3 hybridized orbital on carbon and a 1s orbital, atomic orbital, mind you, in hydrogen. And they form overlap, they form the sigma bond and stuff like that. So, like before, the electron pair geometry will tell you what the hybridization is. And if you see a tetrahedral electron pair geometry, you know that that atom has been sp3 hybridized. And sp3 comes from the fact that each of those 4 orbitals is 1 part s and 3 parts p. And again, I don't know why they made this stuff up, right? I'm just the messenger here. However, that's the origin of it, so now you know what's going on.
A methane molecule forms when 4 hydrogen atoms form sigma bonds to the sp3 hybrid orbitals of the carbon atom.
So in this video, they show those little teardrops, which is kind of like the mushrooms we saw earlier. All right, sometimes people use these teardrops, sometimes they use mushrooms, but those represent the hybridized orbitals. And carbon has 4 of them, 4 sp3 orbitals. So when you make a CH bond, the outer atom just has its regular atomic orbital, 1s in this case, since it's hydrogen. And that overlaps with the sp3, so you end up making the sigma single bond like that. Pretty cool. So again, the takeaways. The electron pair geometry will tell you what the hybridization is. Tetrahedral always means sp3. sp3 means tetrahedral. And when you make a bond, it's the middle atom which is hybridized. The outer atom just stays the same. It just uses its atomic orbitals. So there's no hybridization of hydrogen, for example. It's just the carbon which has been hybridized. And that's where tetrahedral comes from. This is another view just to make sure this is clear. So on the left-hand side, you see 2s and 2p orbitals in carbon. And initially, one of the 2p's is empty, but it's still there. You have 2 electrons in 2s and 2 electrons in 2p. And then they mix or hybridized into 4 equivalent sp3 hybrid orbitals. And you can see in the boxes on the right, all those little arrows are all at the same energy, 1 electron per orbital. So those represent the 4 sp3 orbitals. Now in the last video they showed kind of like a teardrop looking thing. Now they're back to the mushrooms. It depends on the authors and stuff. I think the mushroom is actually technically more correct, but at this level you wouldn't see anything. It's smaller than light. But anyway, I digress. So then in methane, CH4, it's the inner hybridized orbitals that bond with the atomic orbitals of the outer atoms, in this case hydrogen, to make the sigma bonds. So without hybridization, you wouldn't have molecules form, which is kind of a cool thing. This is a summary of the different types of hybridization that are possible. And I want you to look at these terms: sp, sp2, sp3, sp3d, and sp3d2. And these are going to be important. You can always find the hybridization from the electron pair geometry. So for example, if you see one of the examples from the last chapter that's trigonal bipyramid, you know that it's sp3d. And that means that to make one of those orbitals, it took one s, 3 p's, and 1 d orbital to make it happen. And that means because you put 5 orbitals in, you're going to get 5 orbitals out. 5 orbitals will get to the place of maximum distance between each other. Welcome to the trigonal bipyramid, etc., etc. So valence bond is pretty cool for normal kind of operations. You can figure out quickly how the things form and stuff like that. It doesn't have the rigor of molecular orbital theory that we'll talk about here pretty soon, but it is kind of interesting. And again, it works well when chemists are talking at a coffee shop, say, all right, because you don't need fancy computers. You can just kind of talk about things on the back of an envelope, as they say. So it's pretty cool. One more thing. When you make a covalent bond, in this case, you always have to have an unpaired electron on each atom. So like for CH4, you had an unpaired electron on carbon in an sp3 orbital, and the hydrogen had an unpaired electron. And those 2 electrons come together to make the bonding pairs, all right, that we talked about, or in the sigma bond, which is really cool. Also, if you look on the far right, it says remaining p orbitals. Those will be important to us here in a little bit, I promise, but I haven't talked about them yet. We saw boron and boron trifluoride had 1 p orbital. Notice that if you have a linear electron pair geometry, you have 2 remaining p orbitals. We'll talk about this here in a little bit. Okay, so here's a question you might see. It says, what's the hybrid orbital set used by the nitrogen atom in ammonia, NH3? And to answer this question, what you really should do is first draw a Lewis structure. We did this in the last chapter. You can go back and look. When you do this, nitrogen is in the middle of 3 hydrogens, and there's a lone pair on top of the nitrogen. And we talked about how if there's a lone pair and 3 bonding pairs, 4 pairs total, that's going to give it a tetrahedral electron pair geometry. It's going to be the trigonal pyramid molecular geometry. The angles will be about 109 degrees, etc., etc. However, for us, what's important is the electron pair geometry, because tetrahedral always means sp3. So ammonia, in the nitrogen in ammonia, will be sp3 hybridized. The outer hydrogens just use their atomic orbitals, but that nitrogen, sp3. This shows some different combinations of atoms in their hybridization. So the top one there is beryllium dichloride. Now beryllium, boron, aluminum, gallium, those kind of things, they can sometimes be under an octet. And beryllium can actually be really under an octet and be linear. So when beryllium dichloride is made, the beryllium is sp hybridized. And you can see there how the hybrid orbitals, those two little mushrooms, are kind of literally as far apart from each other as they can, which means 180 degrees. So when they bond with the chloride, then you have an sp or hybrid orbital bonding to one of the chlorines, in this case 3p orbitals, making that sigma bond. The next one down is boron trifluoride. The boron is sp2 hybridized to make the trigonal planar structure you see. And the last one there is methane, CH4. The carbon is tetrahedral hybrid, is tetrahedral electron pair geometry. That means that it's sp3 hybridized. And those four sp3 hybrid orbitals get as far apart from each other as they can. They bond with the 1s orbital on hydrogen to make the sigma bonds. Good to go. So this is the kind of question that you might see. I'd like you to try and predict the hybridization in each of the atoms that are pointed to in those little arrows. We'll start in the lower left and we'll go clockwise to the yellow one in the lower right. So the first one there where it says start, you can see it's pointing at the nitrogen, and that nitrogen has 3 bonding pairs, 2 to hydrogen and 1 to the carbon, as well as a lone pair. So 4 clouds means it's going to be tetrahedral electron pair geometry, and like we've seen, tetrahedral is always sp3. So anything that's tetrahedral will be sp3. Going to the red one, it points to that carbon, and that carbon has 1, 2, 3, 4 bonding pairs around it, 2 to the hydrogens, 1 to the nitrogen, and 1 to the carbon. 4 bonding pairs means tetrahedral. Tetrahedral means sp3. Go to the green one now. That carbon in the middle has a double bond and 2 single bonds, a single to carbon, a single to oxygen, and a double bond to oxygen. Double bonds and triple bonds count as one big cloud. So that's 1 cloud to the double bond, 2 and 3 clouds to the single bonds. So 3 bonds around it, or 3 clouds, if you will, want to be as far apart from each other as they can. That's trigonal planar. Trigonal planar is sp2. So that's the one that's a little bit different. But then last of all, that oxygen has 2 lone pairs and 2 bonding pairs, 4 clouds total. It is, you guessed it, tetrahedral. A lot of tetrahedrals in this area, as you can probably see. Tetrahedral sp3. So it's not too bad once you see it. And again, you could also do trigonal bipyramid as sp3d, octahedral as sp3d2, and linear systems would be sp. Earlier I mentioned how some of those have unused p orbitals, and I'm sure you're just dying to know what's happening. So let's talk about those unused p orbitals. And it has to do with multiple bonds. And we saw in the last chapter that sometimes these systems will make double and sometimes even triple bonds. So this is an example of CH2CH2, which is known as ethylene or formally as ethene. Now we talked about how that's an sp2 hybridized system because it's a trigonal planar, stuff like that. But why is that top part flat? Like, why is the double bond just 1 cloud? Why isn't it a second cloud? And that's a great question.
The sigma bonds in ethylene come from the overlap of sp2 hybrid orbitals, 1 from each carbon atom.
Now in the lower right-hand corner, that little video showed the sigma network, the single bonds in the molecule. So each of those little red dots is the nucleus of an atom. So on the outside, you've got the hydrogens, and on the inside, you have carbon. So carbon, if it's trigonal planar, will have sp2 orbitals, and there's 3 of them. So you can see that the red dots there in the middle, they have like 3 teardrops coming out. Each of those is an sp2 orbital. And then what we're looking at here really is the formation of the sigma network. So one of the sp2 orbitals on carbon connects with the atomic hydrogen orbital to make the sigma bond, the single bond that we see between carbon and hydrogen. But also we're seeing here how carbon and carbon can each have an sp2 orbital. They can have overlap, 2 sp2 orbitals to make a sigma bond as well. So in the molecule of CH2CH2 or ethylene, the first bond you see is a sigma bond. So I'm not talking about the double bond. I'm not talking about the top of the two. I'm just talking about one of the lines. I'm going to use the bottom one here. But that's where the sigma bond comes from. The sp2 on the first carbon overlaps with the sp2 on a second carbon. That's where the sigma bond comes from. But where does the second bond come from? I haven't talked about that yet. Well, that last bond, the pi bond, which is what we called it in the last chapter, that pi bond comes from the unused p orbital. So carbon is 2s2, 2p2 when you're thinking about the atomic electrons. And if you have a trigonal planar carbon, like we have in ethylene, then we're going to have 3 sp2 orbitals. But notice how there's one unused orbital left, all right? And that's an unused 2p orbitals. And the 2p orbital on one carbon can combine with the 2p orbital on a second carbon to create a wild pi bond. And a pi bond is an area of electron density that's both above and below the sigma bond. And the closest analogy I can think of is that if you have like a sandwich, all right, the middle part of the sandwich, we'll say peanut butter and jelly, that would be the sigma bond. And then the pi bond would be the bread above and below your peanut butter and jelly sandwich, all right? And it's important to realize, even though you have maybe 2 slices of bread, that's one pi bond. It's both above and below the sigma bond. It's totally wild. This is an attempt, and not a very good attempt, probably as you can imagine, to show that unused 2p orbital. And you can see, which is the blue orbital, by the way, and you can see how it sticks out a little bit above and a little bit below the gold orbitals, which are the sp2 orbitals. And because it sticks out a little bit above and below, it can interact with another p2p orbital to make these pi bonds. It's totally wild. This is like science fiction as far as I'm concerned, even after all these years. It's so cool. But this is what the pi bond comes from.
The pi bonds arise from the overlap of unhybridized p orbitals, one on each carbon. Note that pi bonding electrons are found in a region above and below the sigma bonding region.
So remember how I called it the bread in the sandwich, above and below? That video right there represents one pi bond, and there's 2 regions of it, above the plane and below the plane of the molecule. So again, in the middle there, those are all the sigma bonds, and above and below that sigma network is where this pi bond exists. So we always said in the last chapter how trigonal planar, if you have a double bond like we have here, it was just like one big cloud. And you can see why it is. It literally is one big cloud. It's not a separate cloud like in a tetrahedron. It literally is the same direction and all that kind of stuff, but it's bigger, but it is just one big cloud. So when you have a chemical with a double bond react, it's usually the pi bond which reacts first because it's on the outside. Not all the time, but a lot of the time. So you can see how this is just a wild kind of bonding, but it's pretty exciting.
When we look at both sigma and pi bonds, we see that the CH2 fragments are coplanar and that ethylene is a flat molecule.
So this shows the complete sandwich, if you will, the complete ethylene bonding that's happening when you have a molecule of it. And on the inside, you have the sigma bonds. Those are the individual bonds. And on the outside, both above and below, that's where the pi bond is. So pi bonds are usually a lot bigger than the sigma bonds. They're usually quicker to react because they're easier to get to if something's going to react with them. And that's also why in a double bond, it counts as just one big cloud. It's not a separate cloud because it's right on top of the other ones, which is just pretty crazy. So these molecules are flat, all right? It's just wild, but they have a whole different geometry. Like tetrahedral, you've got all kinds of angle possibilities and stuff. But boy, not when you have an sp2 trigonal planar system with a pi bond, then they're very flat, they're very two-dimensional. Pretty cool. You can have triple bonds. Acetylene is C2H2, also known as ethyne. And in ethyne, you have not just one, but 2 pi bonds. And if you look there on the right side, the top little small picture, that represents one set of bread. It's like above and below the sigmas. But the lower one represents the second pair of bread, and that's like left and right of the molecule. So when you have acetylene, you have these double slices of bread plus the stuff in the middle to make a triple bond. And triple bonds, again, are just one big cloud. It's like tons of bread. If you're not into bread, this isn't your kind of sandwich. But anyway, there's a lot of energy there because all those electrons are floating around. They're pretty easy to get to. So a triple bond is 1 sigma and 2 bonds. So again, if you see a molecule like acetylene with a triple bond, you have to realize that there's 1 sigma, maybe the middle bond right there could be the sigma, and there's 2 pi's. There's one above and one below. So a triple bond is 2 pi bonds and 1 sigma bond, which is pretty cool. This is a question you might see. It says how many total sigma and pi bonds are in acetylene, C2H2, and the Lewis structure is listed up there on the top. All right, so first of all, every time you have a single bond, that's a sigma bond. So there's 1 sigma right there, and there's 1 sigma between that CH right there. So that's 2 sigmas. And then in the middle there, you have that CC triple bond. You have 1 sigma and 2 pi bonds. So triple means 1 sigma and 2 pi. So if you count up all the sigmas, and you have to include the CH bonds, there are 3 sigma bonds and 2 pi bonds for 5 bonds total. That's going to be answer D. All right. So if you see a question like this, just don't forget the CH bonds. A lot of times people forget those, but they do count. They also have sigma bonds and stuff like that. Exciting times.
The carbon-carbon double bond prevents the ends of the 2-butene molecule from rotating freely relative to each other. As one end rotates, the energy of the molecule increases greatly because the carbon-carbon pi bond must be effectively broken. That is, there is a large energy barrier to rotation around the carbon-carbon double bond. Butane can rotate easily about its carbon-carbon single bond because the atoms of its methyl groups repel each other rather weakly. Rotation about this bond is accompanied by a small energy barrier and occurs readily at room temperature. The 2 sides of the molecule are therefore constantly spinning with respect to each other.
This double bond versus sigma bond becomes really important in organic chemistry. And a carbon-carbon double bond in organic chemistry, the names often have E and E. So if you see trans-2-butene or trans-but-2-ene, which is a newer way of talking about it, the E and E means a double bond. But sometimes, a lot of times, you'll also see compounds that have an A and E ending. Those are all single bonds between carbon atoms. So what we have here is a carbon-carbon double bond in the middle part, upper middle part, and we have all carbon-carbon single bonds in the lower graph. And when you look at these 2 graphs, look at the difference between the top energy and the bottom energy for both of these. So for the double bond, it's 230 minus about 30, which is about 200 kilojoules per mole, top to bottom. But if you look in the single bond, it's roughly 80 and roughly 20. That would be a difference of about 60 kilojoules per mole. So those graphs are just basically telling us here that it has a lot more energy to rotate a double bond, which is what the top part is, going from the bottom to the top, a lot more energy to rotate a double bond than it does a single bond, which is what the bottom one is saying. And so in normal room temperature kind of things, the single bonds will rotate like crazy. They rotate kind of like this, like a propeller. They're just going round and round and round and round and round. They'll do that basically all the way down to 0 Kelvin, where all movement stops. On the other hand, boy, oh boy, if you have a double bond, those things don't move, all right? You can make them break and move, but it's very, very difficult, and it doesn't usually happen. So the E and E double bonds are much more difficult to break and make them rotate. And the single bonds, though, are easy to have that happen. We'll talk more about this at the end of Chem 223, but it's something to think about, how this extra pi bond just makes it more difficult sometimes to make one chemical turn into the other.